Hmm. Hey guys, can I get a shout out?
Yep. Hey.
Hello.
Hi. Oh, video is not showing up again. Oh. Hey guys, sorry, can you make sure your audio is muted when you're not talking? Sorry. Thanks. All right, guys. So let's get started today. Let me, I was going to share this other guy. See. Am I sharing my screen? No. Okay, guys, so today we're going to talk about slide deck 4. We're going to move on to slide deck 4, which is sort of basics of CMOS design. But before that, I was going to kind of talk about the our kind of fun side topic of entrepreneurship. So today I was going to talk about um, like finance, which was a very confusing topic to me. And I'm talking not talking about getting financing in, but how to look at money and finance when you're running a company. So let's see. So of course, I always have to say something philosophical. So it's always very confusing to think of the company you're creating. Okay, but for sure, the company you're creating is not you. Okay, for sure. In fact, like if you create a C corporation, it's as if like that corporation has its own legal life separate from you. You'll be a part owner in that company as a shareholder. You may be an employee of that company because, let's say even if you're a CEO, you're still an employee of the company, you're getting paid by that company. It's called a corporate entity, meaning that it's almost its own person. Okay, some people would say it's a sociopathic person, depending on the kind of company it is, but it'd say it's a person. Okay, so I think the best way to look at a company is as if it was a child, okay, that you're sort of bringing up as a parent. That's my model for it. Now, some people are, like more protective of their child. Some people are less. Some people are happy when their child grows up and leaves the house. Some people miss that child terribly. I was the second part. I was like, man, when I parted ways with my child, sold the company, I felt really bad. I felt like I'd kind of lost my kid. It had gone away, etc. Okay, so that's one analogy. The second analogy is, which is the reverse of this analogy of being a parent and a child, is your child is not going to learn how to speak your language. Okay, usually when it's either Spanish speaking at home, English speaking at home, whatever it is, your kid is going to learn how to speak your language. Having a business is the reverse. You're going to have to figure out how to speak the language of the business, and that language is finance. Okay, so that's the first thing, is the way to look at finance. So that's finance is the language of business, pure and simple. Why am I saying that? It's not just a theoretical thing. A lot of what I'm saying is, and you read this stuff in books and all that stuff, and it seems like, oh, it's philosophizing or something like that, but it's not. Business begins and ends with the financial numbers. That's all there is to it. Okay, if you start, the more you're doing like touchy feely guts, you lose sight of the finances, God forbid, and the finances get very, very complicated. It's not good. Okay, you really, the beginning and end of your business is finance. That's how you talk your business, see how it's doing, and you just got to somehow get your head around it. It's not optional. You have to learn that language to be able to run a business, start a business. Okay. So finance is another thing that really confused the hell out of me when I was starting, or from the beginning, because you can go take accounting classes, etc., and that's not the kind of finance you need. I mean, like if you're really hard up for cash, you don't want to hire a bookkeeper or something like that. You want to do your own accounting, okay? But there's like QuickBooks for business, software to do it. There's bookkeeping. I suggest you hire a bookkeeper. They're not that expensive. So like, when you're like taking classes and they're talking about ledgers and, this is this thing, that thing, they're talking to accountants. So you don't need that to run a business. You need to understand finance for non-financial managers. So one of my favorite books, I think it's called, I'll have to, let me know if you guys are interested in this. I'll remind me and I'll get the exact title, but it's just Finance for Financial Managers. Okay. So you don't need to go, and you're just going to get lost. Don't go taking accounting classes. It's not going to help you. You got to take classes or read books about finance for non-financial managers. Okay. So, and as a starting point, that means you have to understand 3 pieces and keep an eye on 3 pieces of documentation, whatever you call it, that you get every month from your accountant. Okay, so I let me see if I can share an Excel sheet as an example. Where is it? So guys, I'm trying to figure out how to share this Excel sheet. Why can't I see this? I'm gonna just try it another way. So you guys are seeing my screen now?
Yeah.
Are you guys
Well, we're seeing the slide deck for stuff.
Yeah. Are you guys seeing an Excel sheet now?
No.
No? Okay, I can't.
No.
No. Shoot. Why? Let me redo this. You guys still with me?
Yeah.
Yeah.
Yes.
Share screen. Ah. You guys see the Excel sheet now?
Yeah, we can.
Okay, so this was, or these are the three main things you have to worry about, okay? So there's the income statement, okay, which is something, it's an accounting thing, but that's the thing you need to do. Income statement tells you what happened compared to the previous month. Okay, and I'll talk about this in some detail. So this is what an income statement looks like. Okay. Then there's a statement of cash flow. Okay. So income statement, cash flow, and balance sheet. Okay, so those are the three things you need to figure out how to read. Because what happens is, so this is again, we would get this from our CPA every month. So they're the ones that are going through and figuring out, creating this. What your job is, as the person running the company, is figure out how to read these documents. Okay, so that again, balance sheet, cash flow, and income statement. So let's take a look at each one of these for just one company. There's different ways to do these, but not that different. Can you guys see this sort of? See the numbers and et cetera here? The particulars don't matter, but so the first part of the income statement is the income. Okay, so here we were looking at, this is divided into services revenue, or these are different customers, and this is how much we got paid from each customer through that month. So it shows our total revenue for that month. Okay, it was $1,182,000. Actually, before I say this, let me tell you guys something about another thing about business. Okay, so most of the time in your business, you don't know what the hell is going on with your finances. It's very confusing. It's confusing as hell. Okay, and somehow when you're a private citizen, it doesn't seem that weird. Like, why are businesses always confused about what's going on in them? Like, I get money in, I have bills to pay. Like, what's confusing about that? Like, but you got to think about, let's say you start a business, okay? So you start a business, you sign a lease with a leasing company, and lease a office for whatever, some amount, $10,000. Let's say, no, say $1,000 a month. Okay, and you sign that for, it's a 12-month lease, let's say. Okay, and then you've got computers, you've got an employee that you got to pay. Let's say, I don't know, you pay them $5,000 a month or something. Okay, so you get a check from your customer to deliver something to him that takes a year to do, right? And they pay you $50,000. Okay, you made an agreement with them. So heck, I'm going to sell you this thing for this service for $50,000. So right now you cash that check, you got $50,000 in the bank, and like normally as a normal human citizen, and again, this gets much more complicated because you got a lot of different incomes, you got a lot of expenses and all this stuff. But in this particular case, you're actually in deep shit, okay? Because normally you'd feel pretty good about $50,000 in the bank, okay? But you're actually like already heading towards bankruptcy here, because your liabilities for the fall to basically earn that $50,000, it's $5,000 a month to pay your employee, which is $60,000. Plus you had $12,000 for rent, God knows what else. So you got an income of $50,000, but your expenses are more than $70,000. And a lot of those expenses are happening in the future, and you, like, how do you account for all this stuff? And so it's like having money in the bank doesn't mean that's how much money you earned that month, because you haven't done the work. And if you don't look at that kind of thing, that income statement gives you a red light, like, hey, you got a problem, because you've only earned from that $50,000, you've only earned $3,500 of that this month, because it's a 12-month project. Am I calculating that right? Maybe not. $4,000 of this month, because it's a 12-month project, and my expenses this month is actually $6,000. Right, $5,000 for the employee and $1,000 for rent. So that's why it's important. Things are happening. You're getting paid ahead of time for work that you got to do in the future, with expenses that might have already happened or might. So it gets very confusing. So let's get back to this. So anyway, for this month, the total revenue was services revenue was $1,118,000 years back. Also had some manufacturing operations. They made $200,000. We had licensed some patents to a company. We made $5,000 from that. Some other material revenue. So in total, we made $1,476,000. Okay, that doesn't mean we got a check for $1,476,000. That's how much we earned. We probably got most of that money several months ago, when the customer signed the agreement with us and paid us an upfront fee to start these projects. Okay, but now we're sort of earning against. That's how much we earned. So we probably have a lot more money in the bank, or hopefully we have more money in the bank. Okay, now that to earn that, we also had a bunch of costs, right? It wasn't free. That's not all the money we put in our pocket, because we got to pay things, we got to pay people. So this is the scary part. So this is called direct. So these are the cost of goods sold, okay? So the cost of goods sold is anything that's directly creating that income. So let's say an engineer worked on that project, that's the cost of goods sold. Or if it was a manufacturing activity, so you created a widget, but you had to buy 2-3 things to make that widget, and those are cost of goods sold. So that's different than, as you'll see later, is you have these basically what's called you call it overhead, or sometimes you call it operating expenses, etc. So let's say the cost for your employees' dental insurance, or if you use a lawyer, etc. That's something you distribute over everything. So that's yet a different cost. But this is just cost of goods sold, is the direct cost to make this income. Okay, so the salaries, we have a bunch of engineers that are making a lot of money. So just to pay the salaries, it's $417,000 a month. Blah blah blah. Materials costs. One nice thing about royalties is there's no cost to that. So the total cost of goods sold was $792,000. So you made $1,476,000. It cost you $792,000 directly to do that. So basically subtract one from the other and you end up at 683,000. Okay, great, 683,000. But still doesn't mean you can put that in your pocket, because again, you have a bunch of other expenses that are more general to your business. For example, your employees get a certain amount of vacation days every year. They may not take it every month, so you got to accrue ahead of time some vacation costs. So every month, it's like as if they took it, and you leave that in the bank, so you have it when they want it back. Insurances, 401k matching. You guys can still hear me? I got this internet being hosed up. Are you still with me?
Yeah, we're here.
Okay, great. So, if you have a receptionist up front, if there was travel expenses, blah, blah, blah. So, this is all the stuff that, all the expenses we were paying for, and the accountants are putting in these different buckets. Long story short, all those total expenses are 333,000. So you subtract that from the 690, and it end up that your total income was $350,000. So out of that million, $1,476,000, you end up making $350,000. There were like, there's some money in the bank, so it made a little bit of interest, etc. But in the end, it ends up being about $353,000 that you earn that month, okay, from operations. So this is also called earnings EBITDA, so it's earnings before taxes. You got to pay taxes at the end of the year, actually quarterly for a business on top of that. But so this is the 353,000 is what like sort of goes in is what you earned, okay, that month. This is like the most important sheet that you have to learn to read every month. Keep an eye on this. This is telling you generally, are you making profits or losses? You want to see, geez, my profits are razor thin. Like, what do I have to do? Do I have to reduce expenses somehow? You're going to start digging into this, trying to figure out what expenses you might need to cut, things like that. So anyways, a million and one things, and there's a million and one ways to analyze this, but this is the level you need to work. So there's an income statement, okay? The next thing you need to do as a startup, you're going to be always cash strapped, okay? So let's say you've got um, this great project, you got it from a blue chip company, you managed to, I don't know, sell this great thing to Google, and they said, hey, you're going to make $10 million, okay, when you deliver, okay? They gave you $1 million up front, and maybe they pay you from milestones, $5 million when you deliver so many, and $10 million, or they give you the final 4 million at the end, let's say. Okay, so now as a startup, this is great, beautiful problem to have, right? So you have that $1 million, blue chip customer, they're good for the money. You don't have to worry about them being good for the 10 million. You just got to produce what you make. Okay. Now let's say, remember, we have a cost of goods sold, right? Every time you make something, it costs you something. So you got to pay for it, right? Now let's say it costs you $300,000 a month as you're producing these things. Okay, so first month you had that $1 million check upfront fee, right? So now you have $700,000 for another month, $300,000 another month. By month 4, like, you're out of cash. The income statement is actually telling you you're making money. Okay, this is the confusing part, which is why you have to keep 3 things in your head. So if you made, so let's say it was a 10-month project, and you had an agreement with your customer that you'd make $10 million for that 10-month project, the income statement would show that you earned $1 million in the first month, $1 million in the second month, $1 million in the third month, and your cost of goods sold in each month was $300,000. So it looks like you're making $700,000 every month. That's what the income statement will show. But the reality is you're actually running out of cash, okay? Until you deliver these parts to your customer, they're not going to actually pay you the cash. And you can't just tell your vendors that are giving you the parts to make this thing that to wait for you to have faith in you. They want their cash right away usually, okay, or 30 days or whatever. So you could easily get into a situation that although the income statement says you're making money, and in fact, as a business, like, it's a pretty good thing, you may just run out of cash. And as soon as you run out of cash, you are screwed. End of story. You're gonna just have to fire all your employees, turn off all your lights. It's like no, you know, banks will turn their backs on you. Anyway, bad situation, bad, bad, bad. So you also have to watch your cash like a hawk. So that's why you need an income statement and look and the cash flow. You have to keep a very tight eye on both of those. Okay, balance sheet. Honestly, I only looked at this at the end of the year. Maybe different businesses are different. Basically, it tells you what the business is worth. So, you know, it's in this case back then, I mean, this is the business is worth from a financial point of view. It doesn't mean this is what somebody's going to pay you for your business, because there's a lot of like, this doesn't, if you had, you know, 50 patents that were extremely valuable, it's not going to show up as a dollar amount in your balance sheet. Balance sheet just says you have X amount of dollars in the bank, you have X amount of fixed assets, which are like furniture and equipment, etc. And say you owe a bunch of money to some vendors, etc. So you subtract one from the other, and you end up with what's your total equity in the business. In that case, it said that we were worth $9 million as a business. So in that year, we sold our business for $50 million. So because there was that $40 million worth of intellectual property and blah, blah, blah that we developed. So this balance sheet is just telling you, you know, if you were a, I don't know, donut shop or something that there was no IP or key customers or those kind of things, what it would mean. So I never really paid much attention to the balance sheet, but it's something good to look at maybe once a year. Okay, guys, so that was, boy, I spent way too much time on that, so sorry. But is this of interest for you guys, or is it just boring as hell and you guys don't care? Waste of your time.
It's pretty interesting. Professor, I had a quick question.
Yeah.
Does this sheet include the ARR in here?
And what, sorry?
The annual recurring, what is it? The ARR, like revenue, my bad. Annual recurring revenue. I didn't notice it.
Or like a recurring revenue?
Mm-hmm.
It would show up in the income statement. If you had that, it would show up in the income statement, I think.
Okay.
And it would probably show up in cash flow. But so the main message I have for you guys, I have two messages for you guys about this and entrepreneurship. One is don't focus on all of finance. Just focus on, because this is a very broad topic, and don't, you know, for years I would go to these accounting classes and, you know, my eyes would glaze over and no idea what, you know, what's going on, didn't get very far. And I was like, it's like a hopeless situation. God, I'm never going to be able to deal with this. But as a business manager, these are the things you need to, you don't need to figure out all this stuff. You can hire people to do that. And it's, again, it's not very expensive. But you need to understand what the numbers finally mean. And the income statement, cash flow, and the balance sheet are your ultimate friends. Okay, I think this is, like, in my opinion, this is hugely important, whether you guys are going to run a business. I mean, even if you're not, at some point you might own stocks, things like that, as just, you know, investors, whatever, in your 401k. And you want to be able to read, these are the documents you typically read for a company. So you'd go to, you know, if you want to know how some company you want to invest, how Nestle or Pfizer is doing, you go basically read their income statement, the balance sheet, cash flow, and that's how you figure out how they're doing as a business, where it's going, etc. Okay, so thanks for your patience, guys. It took me a little bit, that went a little bit further than I thought. So now let's get to the business at hand. So let me share screen. Okay. So let's introduce CMOS gates. Okay, so what is it? This is like a little bit more, even more focused than this. This isn't just CMOS gate. This is so-called static, because it's CMOS logic families. Okay.
Professor?
Yes.
Where's on the Excel sheet?
Oh, thanks for, thank you. Great. Okay. So static CMOS logic gates. Okay, so what does that look like? So let me draw it for you guys. So let's say we have a 4-input NOR. Okay, so if you were gonna draw it as a logic gate, the NOR would look like this. Everybody's familiar with the NOR functionality? Anybody not familiar with the NOR gate? Okay, everybody's good. Okay, so here's what it looks like. Okay, so, and we'll get to seeing how you would do that. You have a bunch of N MOSFETs. Remember an inverter. Actually, I don't know if you guys, we talked about this. So a CMOS, so this is a symbol for an inverter. So this is in, out. And if I was gonna draw this inverter as a schematic, it would have a P on top and an N on bottom. Their inputs would be connected and their drains. So the gates would be connected together and be the input. Their drains would be connected and be the output. So for a NOR gate, would have a bunch of ends connected to ground. Their sources are all connected to ground, and their inputs are connected to the inputs A, B, C, D. Okay, and their drains would all be connected together. Okay, and then I would have a bunch of P MOSFETs. And we're going to talk about how this works and how you can actually design this. But you have a bunch of P MOSFETs hooked up in series, and your output would be here. Oops, sorry. Okay, so this is how a 4-input CMOS NOR gate looks. And if you were gonna do like a really simple model of CMOS logic, you'd say, okay, well, I'm gonna have, let's say I wanna have an NMOS. And the NMOS, when I make it a really simple model, okay? If, so this is gate, drain, source. So if the gate is high, let's say high, I'll just call it 1, right? It's gonna be a closed switch. And if the gate is 0, it's gonna be an open switch. Okay, so let's say if I did that. Now let's look at what this bottom part would look like. Okay, so I'm just gonna copy this guy. So if I just look at these N MOSFETs, what would it look like? It'd be a bunch of switches. With, their gates were, basically they're controlling things are these gates. You guys see what I'm doing? Okay. So this kind of looks like they're hooked up in a OR configuration, right? So if any of these guys is closed, the output goes to ground. Okay, if any one of these is on, the output goes low. Okay. And if I draw these as switches, let's for the sake of discussion say this was the same thing. But now if I have P MOSFETs, PMOS sort of acts like the inverse of NMOS. This is like a really, this is not the model to think about, but like if you were gonna look at it like this. So it works the reverse, right? If the gate equal to 0, it's a short, and if the gate is equal to 1, it's an open. Okay, so if I was gonna look at the top guys, whoops, it would look like a bunch of switches like this. Um, okay, so in this case, all for this to get a high output, to get an output that's VDD, all of these guys need to be closed. Okay, so all of these guys need to be 0 for me to get VDD connection to the output. So basically all of them have to be 0 for me to get a high value, which is a NOR functionality. Okay, so basically as long as any one of these A, B, C, D is high, you'll get a 0. Okay, and only when all of these guys are 0 will I be able to get a high. Okay, so this is an example of sort of like how a CMOS gate works. So let's look at it. So generally, what does this have? So it has a pull-up network that goes to the supply voltage. Okay, and the pull-up network is made out of PMOS transistors, and it has a pull-down network that's made out of NMOS transistors that finally go to ground. Okay, so this is what every CMOS, static CMOS gate looks like. Okay, so what you have is a network of PMOS transistors that pull the output up to VDD, or try to, when they're all on, or some are on, depending on how you design it. And then you have a network of NMOS transistors that they're not connected to VDD, they can only pull down, okay? So they're pulling things to ground. And the inputs are connected to both the P and the N, to both the pull-up network and the pull-down network, okay? So again, this is static. This is a static logic to separate it from dynamic logic. The reason I bring up the dynamic logic is because in a CMOS process, you can do the kind of logic that you can really make the logic very fast and very low area by doing sort of a pre-charge function and just do discharge, etc. I'm not going to that right now, but it's possible. This logic will stay, the value will stay, if the inputs stay constant, the output is going to stay constant. You don't need to do pre-charge functions. It's not going to drain away. So that's why it's called static. Okay. So let's see. So the other stuff to think about here. So again, going back to our example. Okay. When the pull downs, these are the N MOSFETs, are on, okay, the pull-ups are going to be off. So no, I'm sorry. What am I lost focus here. So here's two cases, right? When pull downs are on, so the NMOSs are all on. Okay, if the pull-ups are off, okay, the output is 0, right? Because basically this guy's off in this case. And the output, these guys are on, and the output has to be 0. Okay, so when the pull downs are off, meaning that these guys aren't doing anything, okay, and the pull ups are on, the output can only be a 1 because there's nothing pulling the output down. The pull up network is pulling it up, so you get a 1 value or a 0 value. So pull downs on, you get a 0. Pull ups off, you get a 1. If somehow the pull downs could be on and the pull ups could be on, you would end up with a problem because the pull downs would try to pull down this thing, the output, and the pull ups would try to pull up the output. So you end up with an undefined output value. Okay, so you never want that to happen. You never want both this and this to be on at the same time. Okay, because you get an undefined value. Just then you'll get some value out here depending on the resistive strength of this guy versus this guy. Okay, so that's this case here. Now, if the pull downs were off and the pull ups were off, so if they're both off at the same time, this output would be floating. So you're no longer sort of in a static logic function 1. So this would, discharge or charge up because it'd be floating. So it change with time, change with temperature. You could get any kind of noise in here. Basically, it's another undefined state. So you never want to be in a situation where both of these guys are on or both of them are off. So the only way this logic works is either the pull-up network is on or the pull-down network is on, but never both at the same time. Okay, so that's this basic philosophy of a CMOS static logic. Bunch of P MOSFETs to pull up network, bunch of N MOSFETs to pull down, and you do not want them, you only want only one of them to be on at one time. Okay, so now let's see these kind of functionalities. So when you have, I talked about this a little bit already. If you have, two N MOSFETs in series, like here, it looks like a AND functionality between A and B. Okay, if both G1 and G2 are high, you get them to be on. But as long as, so G1 and G2 would lead to an on situation from A to B, but any other combination gives you an off. So that's like a AND functionality. Okay, same with the P MOSFETs, except the inputs are inverted, right? Only when they're both zeros do you get going through 1. And any other combination would make it off. Okay, now sort of OR functionality, if you have two N MOSFETs, okay, if the inputs, either one of the inputs is on, so if either one of the inputs is on, this combination is on. And if, only if both inputs are off, do you get this switch to be off. And sort of the complement of that is P MOSFETs, is that only when both inputs are on do you get an off function, okay? In all the other cases, it's on. Just because a PMOS, again, in this view of a PMOS or NMOS as just a switch where all that matters is the gate, state, not the source and drain. As we'll see, the source and drain also matter, but in this view, that's kind of what happens. So it's interesting that you see that this is a complementary state, okay? So that an NMOS, okay, notice how this is a complement to this, okay? So in this case, when G1 and G2 are on, you get an on. In every other case, you have an off. And in this case, it's completely the reverse, right? When G1 and G2 are on, it's the only case where it's off, and all the other cases are on. So you can think of this and this, or this is P MOSFETs hooked up in parallel. You can think of the P MOSFETs in parallel as being a complement to N MOSFETs in series, okay? And vice versa. You can see P MOSFETs in series, okay, as being a complement to N MOSFETs in parallel. Okay. Any questions about that? So what that means, if you want to create a situation where you have, let's say you want to, again, I'm going to sort of do this over and over again. Let's say you want to build a NAND gate. Okay. So if you wanted to build a NAND gate, you would have, let's say, 2-input NAND gate. So these are the inputs, and here's the output for a NAND gate. I always have to remember. Right? I think that's right. Okay. So what you would do is you would have you'd start by building a AND functionality with the N MOSFETs. Why AND? Because A and B would make this thing on. So that's an AND functionality. But remember, this guy is hooked up to ground. So it passes a 0. So it actually looks like a NAND because A and B have to be on to get a 0 on the output. Okay. And then on the pull-up, now I need to find a way to get a high on the output. So the pull-up, I need to put the complement of this functionality in the form of P MOSFETs. So the complement of N MOSFETs in series is P MOSFETs in parallel. Okay, so basically what I do is I put in and the inputs go to the same inputs. So these are P MOSFETs in parallel. And that ends up being my 2-input NAND gate. If A and B are both high, both of these guys are off, and I get a ground on the output, so I get a 0 on the output. If either A or B is a 0, if either A or B is 0, this path is off. And if either A or B is 0, this path is on. One or the other is on, or they're both on, in which case I get a high on the output. Okay, so this is a CMOS NAND gate. Any questions about that? So this is like another, basically this is what we're talking about here. So what you want to do is, if you want to design a CMOS gate, first thing you do is you design the pull down network, and N MOSFETs, when they're hooked up in series, it's type of an AND functionality. When they're hooked up in parallel, it's kind of an OR functionality. But because in CMOS logic, they're hooked up to ground, you get the complement of that. So series would be NAND functionality, and parallel would be NOR functionality. So like if you're looking back here, when we had the NOR gate, we had them in parallel. Okay, so it sort of gives you a NOR functionality. Okay, so that's where you start, and then you basically take the complement of that in the form of CMOS transistors and the complement of NAND gate. So the complement of series is parallel. So in this case, you'd have two parallel devices being your pull-up. Okay, so that's kind of our rule. Okay, so this got kind of mangled, but so you can also build compound gates by mixing up these functions. Okay, so let's see, let me run this guy. Let's try that. So you can mix, stuff that's pretty complicated. For example, what, let's see, let's try this example. Okay, guys, so let's say in CMOS, you wanted to design a gate that did the following, that the output would be A and B, or C and D, and the whole thing inverted. Let's say we wanted to build that. Okay, why don't you guys take a shot at it, okay, for a few minutes and see what we can come up with. Again, remember that for N MOSFETs and functionality, A and B would show up like this, would be series, and OR functionality is like that. And for P MOSFETs, so this is OR, this is AND. So in P MOSFETs and functionality, the complement of that would be that. And the complement of this would be that. Okay, so why don't you guys give it a shot for a few minutes? Okay, guys, let's try to solve it together. Any volunteers to help me figure this out? For picking unfortunate. Volunteers going once, going twice. Okay, I'm gonna pick Samuel because you got a nice picture, Samuel. You got a nice smile.
Oh no.
So you should have put an uninviting picture on.
Right? Yeah.
Yeah, too late. So let's help me try to do this. Okay, so let's look at this guy, A and B. What would
Yes.
okay? What would that look like for N MOSFETs?
I'll use the first one.
Uh-huh. Right.
Um,
You mean here?
yeah.
Okay. So you
Yeah.
draw A and B. Okay. And then one is the
And
same.
then, yes, and then yeah. And I'm thinking to use the plus, so the second one, so the top right ones, like combine them like that.
Yeah. So let's say we do this and this. Okay. So this is C and D. So how would you combine them?
Uh,
So that's this guy,
like,
this guy, this guy, this guy. Yeah. Go ahead.
uh-huh. And like the top and bottom part.
Yeah. So you would just you would basically look at this guy as being one expression, this guy as being the other expression, and to do an OR function, you hook him up like an OR. So you got to write
Yes.
it up like that and like that. Okay, and that gets ground. Okay. So now, whoops, I picked the wrong thing. Let me move this down. Okay, so now we need to build the complement for the pull-up network, right, for the PMOS FETs. So what do we do there? Let's
Can
look
we
at,
just
go ahead.
so I think this is part when I got confused. So originally I was thinking about just put the inverter like for all of them, but then I don't think that will work.
Can you say that again?
Like just put the dot, the circle on all of them.
Oh, I see. So up here, what you're saying is you would like do something like this.
Yeah, but I don't know if that's right.
Yeah, so it's actually not, but the reason is, I think you're on the right path though, is remember that on the pull-up network, it's not the same as the pull-down network. It has to be the complement of the pull-down network. Okay, so the pull-up network is the complement of the pull-down network. Pull down. So this guy is not gonna can't be the same, but it has to be the complement of it. So what does that mean? So we said if like a AND type functionality is like this for NMOS, but the complement of it in PMOS is these guys in parallel. So so if you have this in NMOS in the pull downs, you have to build this in the PMOS. So what you'd end up with is this and this. So this pair is the complement to this pair. So just remember that if you've got this thing on the NMOS side, it's always easier to think of the NMOSs because it's sort of more straightforward. You got that, you got to make the complement of it in the PMOS.
Okay, I see.
And then you do the same thing for the C and D. Okay. Okay, now what?
Gotcha.
But now,
Okay.
okay, so we're still not done. Now we gotta sort of remember we had this OR function, which looked like this, which these two would be hooked up like this. So now we need to get the complement of that OR function in CMOS, in the PMOS and the pull-ups. So what do we have to do there? What's the complement of this guy is this guy, right? So here's where it gets a little tricky. So what we have to do is put these guys in series, in series with this guy.
Does it also work if you put AB above the CD one?
Yeah, that worked. It'll work the same way. And this is out. Okay, Samuel, thanks for being a good sport. You're off the hook for a little bit. I'll pick somebody else next time. So who just spoke about wondering if this was on top or bottom?
That was me.
Okay, sorry, I can never tell who's that. But what's that?
It was Connor.
Oh, Connor. So it can be Connor, and when you're talking about a DC type of situation, it doesn't matter at all which one's which. We'll see much later, maybe 4 or 5 weeks from now, that one of these, the speed of these different inputs, the amount of delay from the input to the output is not the same for all of them. So if, for example, one of them is like switching constantly or needed to have a really fast transition, that's when it would matter where you would put them in the stack. But from a static situation, when you're not looking at timing, it doesn't matter at all. Okay.
Okay.
Okay, guys, let's do one more. Now this one you're going to be able to cheat, but try and control yourselves, because the answer is written below, but don't look. So give this another shot. So the output is A plus B plus C and D. Okay, and try that one. Give that a shot for a few minutes. So I've already picked my next victim, so it's a question of who it is. You guys don't know. Okay, any volunteers?
I'd like to give it a shot.
Okay, cool.
So, well, obviously, as before, A, B, and C are all connected in parallel, I suppose, because they're ORed.
Yep. So A, B, C. Okay.
And then because it's ANDed with D, you have to put that, I suppose, serially. What I did is I just drew like a big old box up above and below the A and B and connected C there.
Yep. So like this.
Yeah, right there. Yeah.
Okay, let me ground this. Yep. Oh, no,
Yeah,
sorry.
and that's the-
D. Sorry, this is D. I'm sorry.
Oh yeah, sorry, D.
D.
And that's the pull down, and then for the pull up, invert it. So A, B, and C would be serial, while D would be in parallel with all of those
Yep. Dead bang.
while inverted.
Yep, exactly. So whoops, these are all bubbles on them. And this is D. Yep, that's it. That's the answer. Thanks. You just saved Megan. Megan, say thanks, because you were gonna get picked.
Oh, thanks. Yeah, I'm here.
You were gonna be next. It's that guitar picture. Okay, so that's how you would design complex gates. It's the same way when you're designing NANDs or NORs or whatever, but you can even make more complex gates in CMOS. So that's one of the nice things about CMOS is, let's say you had a complex logic function. Sometimes it's more efficient to do it. They call these complex gates, meaning that they're not your usual ANDs and ORs and XORs and stuff like that. But sometimes these end up being more space efficient. You can have fewer transistors, and you can't make them too big. They start getting slowing down if you make them too complicated. But anyway, you can make some complex functionality with a CMOS gate. But you can do the same thing with NMOS. Sorry, with NOR gates, NAND gates, whatever. Same thinking. Okay, so that's the first thing, is just thinking about NMOSFETs as being on devices. So this is sort of the first level thinking of, again, NMOSFET as being on or off, just depending on, I don't know what I'm going to call this, G, depending on the G being 1 or 0. Okay, so this is, and then same with okay, in this case, maybe, okay, G equal to 0. Okay, so this is like a very first level model that got us this far. Okay, so the next complication is that it turns out that N MOSFETs and P MOSFETs are not equally good at, it doesn't, like, it matters what A and B are, like if they're zeros or ones. Okay, this is what this means, is that N MOSFETs, and we'll, in a few classes, we're going to get to why this is specifically. So, okay, let me take a step back. Sorry, guys. So the step back is an NMOS transistor. It's actually like a very complicated beast, right? We drew this. So the gate, source, drain. So this was N plus, P minus, okay? And if I did the voltage versus current characteristics of this thing, I would get, let's say this is the drain source voltage, this is the drain current. I get these curves for different gate source voltages. And then if I plotted the gate source voltage, we're going to get into all this stuff. Let's get something like that for different drains. Okay, so it's this like nonlinear device with lots of different, this, as you'll find out, this looks like different resistance, different impedance values from A to B, and different, like it's like a giant, complicated, fun mess. Okay, now we're trying to, when we're using it as a logic element, the first thing we did was just said, oh, like this just looks like a switch. Okay, we're just going to use it like a switch and pretend like everything's good. But very quickly you run into complications, and this is the different complications. So the very first model was switch, it's on, we're good to go. But the reality is, and we'll see why this is the case in a little bit, is that N MOSFETs are good at passing zeros through them. Okay, so if the gate was a 1 and my source was 0, I would pass the 0 really good. Okay, now if the gate was a 1 and I was trying to pass a 1 through an NMOS, this would turn into a, I don't know what I'd call it, a crappy 1. You wouldn't quite get a real 1. You'd get a degraded or a weak 1 passing through, because N MOSFETs are just not good at passing logic 1 or a high voltage from source to drain. They're really good at passing 0 from source to drain. Okay, same with PMOSFETs. PMOSFETs are really good at passing a logic 1 from source to drain. They're really good at passing high voltages from source to drain. But they're really bad at passing. If you ask a PMOS to get an output, to get a high value out, it's going to give you the exact high value. If you ask it to put a low value out, it's going to give you a degraded weak value, and we'll see what that means. Okay. So, and this is the reason why the NMOSFETs are only used for the pull down network, because all we're asking of the pull down network, we'll go up here. All we're asking of the pull down network is to pass low values, right? Notice the pull down network never deals with a high value. It's either off or it's passing a 0 or a ground voltage to the output. Okay, so same with the inverse of this for the PMOS network. We're never asking the PMOS network to pass a 0 through it. It's either off or passing a high value or passing supply voltage to the output. Okay, and that's why it's built like this, is because of these transistors. The NMOSFETs are good at passing zeros. The PMOSFETs are good at passing ones. So that way you're always guaranteed to get a good solid output, either a good solid 0 or a good solid 1. Okay, so that's the first thing that you get out of these, the fact that the NMOS is good at passing a 0 and the PMOS is good at passing 1. The second thing is that sometimes it's another element of the static CMOS technology is called a pass transistor. Okay, so a gate looks like, again, this pull down network and a pull up network. So pull down, pull up. Okay, sometimes you just want to use a pass transistor. Let's say you were building a multiplexer. Okay, so what does a multiplexer looks like? This is a sort of the logic thing for the multiplexer, and it would have a select, and if the select is how should I draw this? If the select is 0, then the output gets A. You know, if A is 1, and the output you get 1. If A is 0, the output you get 0. And if the select switch is 1, the output would be B. So another way to think about it is select 0, you'd get this guy going to the output. And if you wanted to get select 1, you'd get the B to the output. Okay, so to make this with like NANDs and NORs and stuff like that is, you know, you'd need a lot of transistors. Okay, so looks like an easy thing to do if we were just thinking about switches is just make this out of 2 transistors, say 2 NMOSFETs. So they get A, B out. So this is select so make this, sorry, make this, what am I doing? Make this one a PMOS. So make select, and select looks like you could just get away with this, right? So if select was high, the PMOS would be off, the NMOS would be on, I'd get A to go to the output. And if select is low, you'd turn this guy on and send B to the output, and this guy would get turned off. Okay, so it looks like that should work. the problem is, so that's a much simpler multiplexer than like, building this thing with a bunch of NANDs and NORs, right? But the problem is, if A was a high value, this thing would give you, and if select was selecting A, you'd get a degraded high value. Okay, you wouldn't quite get a 1. You would get something lower voltage than 1. So it would degrade your noise margin. That's why it's called degraded. Okay, and vice versa for the P. If B was a 0 value and you selected it, you wouldn't quite get a 0 out. You'd get something degraded. So again, a bad noise margin. Okay, so that's why instead of doing that, you actually add one more transistor. So if I was going to make a mux out of this, what I would do is oops. Okay, so what I would do is I would put, oops, how did I do that? I'll just draw it. Nah, it's gonna confuse you guys. Okay, let me just start from scratch. Got too big of a mess. So you'd have A select, so that's what we had from before, except now I'm gonna add a PMOS, so when I just flip it around, this is typically done. Still goes to A, then I'm gonna put select bar on that and connect these two. Okay, and I'm gonna do the same thing with B. So this is select. I'm gonna put an NMOS on B and put select bar on it. And then I'm gonna connect these outputs. Okay, so now look at this. So if select is a 1, okay, select is 1, select bar is 0. I have to create select bar, okay? If select is 1, select bar is 0. So that means if A, and then both of these guys turn on, okay, select, so the gate of this guy is 1, the gate of this is 0, so that means they both are on. This one, the gate in this case will be 1, so that means it's off. And S bar ends up being low, so this is off. So this guy's off in this case when select is 0. Sorry, did I draw this right? No, I screwed it up. So select is bar. There we go. So select. Yeah. Okay, so let's redo this. So if select is 0, select is 0, I want A to go through. Okay, so select is 0, this NMOS is on, this PMOS is on, this PMOS is off, this NMOS is off, so A goes through, okay? Now, because I have an NMOS in parallel with a PMOS, if A is a 0, the NMOS will pass that 0 very well, okay? If A is a high value, the PMOS transistor will pass it very well. So either way, I get a non-degraded 0 or a non-degraded 1 because these two are working where when the NMOS is weak, the PMOS is strong, and vice versa, okay? And same with this. So basically you end up with this thing called a transmission gate. So you never, not never, but like at your own risk, would you use a pass transistor, either N or a P by itself? You always want to use, in a good solid design, you always want to use this transmission gate, which includes both an N-type transistor and a P-type transistor in parallel as something that's passing a voltage through. Okay, so that's another permissible device, logic device now in a CMOS logic family. So first we had the gates with the pull down and the pull up. The other device that you can use as a legitimate logic device is a transmission gate. So it can pass zeros and ones. Okay, so sometimes, so another logic function that you'd like to have is, let's say you had a bus that you wanted to drive, right? So you had a bunch of outputs. So you had, let's say, a bunch of blocks. So, you know, logic block A, logic B, logic C, that they all wanted to use this device, this bus in turn, okay? So the problem with like a bus is not all of these guys, if all of these guys were driving a bus, remember that in CMOS logic, the output is either a high or a low. You don't get intermediate values. So this would mean if I have all of these hooked up with CMOS buffers, that start fighting each other. If logic, you know, if this block wants to drive this bus, this logic B and C are also trying to drive the bus. Okay, so I have to find some way of turning these guys off. And if all I had was regular CMOS logic, there's no ways to turn it off, right? You either are, remember our rule was, you either the pull down network is on or the pull up network is on. They both can't be off, okay? So you need to something that allows you to do that in the case of driving buses and things like that, okay? So that, in that case, you have this thing called a tri-state buffer. And why is it called a tri-state? Is because it has both 0, a 1, and then floating as a function, or high impedance, so-called. So here, if you look at this guy, okay, when the enable is 0, if A 0, you'd still get a Z, which is neither 0 nor 1. You can think of it as a high impedance state where the output resistance is infinite for this gate. So it's just sort of like just floating, okay? And so it doesn't matter what A is in that case, it's floating. When enable becomes a 1, then it's passing A, okay, to the output. So that's a tri-state gate. And so you can do that using the sort of a pass transistor, or sorry, a transmission gate, okay? So if enable is high, enable bar is low, so it means both of these guys are on, and I can pass either a 0 really good or a 1 really good to the output. Or if enable is low, enable bar is high, and both of these guys are off, and this point is just floating. You only really want to do that in a like, think about that very carefully, because normally it would be a very dangerous state. Something else needs to drive that node if this guy is not driving the node. Okay, so always in a tri-state case, you want to make sure that it doesn't stay tri-stated, that something else is driving it. Okay, but anyway, you can get that functionality. And the way you get a tri-state, you know, you can either get it 2 ways. One of them is this way. This is called a non-restoring tri-state. This is because if you have this as the output, you have sort of a, you don't have a lot of drive coming into this. So the other way to do it is also just put it in sort of series with your inverter, your enable. So then either you can push high or push low. Okay. Multiplexer, we already talked about. Uh-oh, sorry guys, I'm way over time. I lost track of time. So let's stop here, and then we'll proceed for the rest on Tuesday.
Wait, Professor, you have office hours tomorrow morning, right?
I do, yeah, and I think it's 9 to 11 or something.
Yeah, it is. Is it cool if I show you my schematic for the project?
Of course, yeah.
I need some help trying to run it because I keep running into error messages.
Sure.
And I even tried putting like the sulfur configuration and everything, and I took all the extra precautions. I just don't know why it's not working. So
Okay.
yeah, I'll probably swing by your office hours tomorrow.
Yeah, please do. Are you using LT Spice?
Hello?
Yeah, are you using LT Spice or are you using some other spice?
I'm using LT Spice.
Okay, so if it might, you could send me also like tonight or tomorrow morning beforehand. You could like email me or
okay.
so I can take a look at it before we talk and try to figure it out also.
Yeah, that'd be good.
Okay, sounds good.
Bye.
Okay, guys. And you have no other questions?
Why it's not working?
What's that? Yeah, it's probably something simple. We'll see. I hope. Okay, guys. Have a good weekend.
Thank you, Professor. Have a good one.
Professor.